Alrighty, good evening, and welcome to our Chem 400 office hours. Although office hours technically are not starting just quite yet, I am going to do our part 2 lecture tonight of chapter 5, which is gas laws, and then follow up with open office hours. So, and I think, checked my emails periodically throughout the day. I think there's like one office hour email question, and then which I'll get to. And of course, I'll take live questions first, prioritize the humans who are here. But okay, so we left off on Wednesday of last week. And again, this is Chapter 5, which is all about the gas phase. We left off on Wednesday. Today's Monday. It's been a long day. We left off on Wednesday talking about we were talking about the combined gas law, and how that led us to asking, what does that constant equal when you have pressure of a gas multiplied by volume of gas divided by the product of temperature and the moles of gas in that sample? It led us to something called the ideal gas law. And the ideal gas law is pressure times volume is equal to moles times the ideal gas constant times temperature. All right, and just by way of review, the ideal gas constant is represented by the symbol R, and R is equal to 0.08206. The units are liter atmospheres in the numerator. Oh, that went off the page. There we go. Atmospheres over mole Kelvin. All right. So that is the ideal gas law and the ideal gas constant. You will always know R, right? You always have the value for R. It's a constant. And as a result, if you also know pressure, volume, and temperature, the pressure, volume, and temperature of a gas, then you can find the moles of gas. All right? And that is what gives us an entry into stoichiometry using these quantities of a gas, pressure, volume, temperature, in doing some stoichiometric calculations. All right, now let's go ahead and so I left with a couple of examples at the end of my first lab lecture, and we're going to go ahead and lead with those. So the first one asked us to find what is the volume of 1.00 moles of helium gas at STP. All right, and STP, we learned, is standard temperature and pressure, which is a pressure of 1.00 atmospheres and a temperature of 273.15 Kelvin. All right, and you'll notice that we're being asked to find volume, and we're given, right, moles, pressure, and temperature. So this looks like a job for PV equals nRT. We have moles, we've been given moles, we've been given pressure, and we've been given temperature, and you always know what the ideal gas constant is. So we've got one algebraic step to do, we've got to divide both sides by pressure to isolate the volume of a gas. And so we get volume is equal, the volume of the gas is equal to the moles times the ideal gas constant times temperature over pressure. And now we can plug in our quantities, 1.00 moles times R, which is 0.08206. You'll notice this has 4 sig figs. You may be used to using a value for the ideal gas constant that has fewer. In this class, you need to use the value for the ideal gas constant that has 4 sig figs. Otherwise, you'll get things wrong. So make sure that you're using 0.08206 as I am here. And then let's multiply by temperature. 273.15 Kelvin, all over our pressure of 1.00 atmospheres. All right. And you'll notice that pressure cancels, atmospheres, moles cancel, and temperature cancels, right? Kelvins cancel. And we are now good to crunch our numbers. The only unit left standing is liters, and that's good because that is our volume. All right, so multiplying all these things together, we have 1 times 0.08206 times 273.15 divided by 1. And you'll notice that the volume, hang on 1 second, my kids are kind of being loud. Sorry about that. All right, so our volume here is 22.414689. However, based on the sig figs that we used, our pressure only has 3 significant figures, so we have to round our answer to 3 sig figs. So this comes out to be 22.4 liters is our answer. This quantity is kind of special. This is called the molar volume of a gas. And the reason why it's called the molar volume of a gas is because you'll notice that it is the volume that 1 mole of an ideal gas will occupy. So you'll see that kind of thrown around, 22.4. If you do the homework, you'll notice it comes up every once in a while. And then that's where it comes from, because when you do the calculation with the ideal gas law, for 1 mole of gas at standard temperature and pressure, it comes out to 22.4 liters. All right, let's do the second example that I left you with before kind of forging ahead into new territory. So the second question is I asked, let's switch this to black. I asked what you to find the density of nitrogen gas, the density of, if you had 1 mole, 1.00 moles of nitrogen gas at STP. All right, now here, first let's look at what we're trying to find, right? And it's right up there. We're trying to find the density of N2, which density is equal to the mass, right? Grams over volume, right? Mass over liters. Now, you'll notice what we're given So we need to find two things. We need to find grams and we need to find our volume. And we're given our moles of gas. Moles of gas, we have 1. We're given our temperature, right, because we're at STP, so our temperature is 273.15 Kelvin. And our pressure is 1.00 atmospheres. All right, so this is what we have to work with, and you'll notice that there's a similar pattern, right, to the problem we just did. In our denominator here, we need to find liters, and we know that we have the ideal gas law, PV equals nRT, where we have pressure, moles, temperature, and we always have R. So we can use the ideal gas law to find our volume. All right, but what about our numerator? What about our mass? Well, we're given the number of moles of N2 we have, so we just have to convert grams to moles, all right? So that's how we get our numerator, and then we use the ideal gas law to get our denominator. So first, going from finding our numerator, we have 1 mole of N2, and we need to convert from moles of nitrogen to grams. Nitrogen, the atom, has an atomic mass of 14.01, so the molecule will have a mass of 28.02 grams per mole. Moles cancel moles. And so that gives us a numerator, right, of 28.02 grams. And now, hang on one second. Our quantity of moles only has 3 sig figs. So our value for our mass only has 3 sig figs. I'm going to wait around till the end because that's the correct way to do things. But I put those 3 lines to remind myself that that number only has 3 significant figures. Now we need to use the ideal gas law to find our volume. So we have PV equals nRT. We need to isolate volume on one side of this equation, so we're going to... What am I doing? We're not dividing by volume, we need to divide by pressure. There we go. I apologize if you can hear my 2-year-old in the background. It's a little past his bedtime, but he still needs to eat dinner, so, you know. There may be some baby tears in the future, in the background of our lecture. We'll see. So volume is equal to our moles times the ideal gas constant times temperature over pressure. Moles, we have 1 mole of nitrogen gas. The ideal gas constant is 0.08206 liter atmospheres per mole Kelvin. Times our temperature, which is 273.15 K, all over our pressure, which is 1 atmosphere because we are at STP. All right, now you'll notice that pressure units cancel, our moles cancel, and Kelvin cancels. And so this will give us a volume. Wait, this is going to come out to be exactly the same. 1 times 0.08206 times 273.15 divided by 1. Yep. Our volume, which is the denominator of a density calculation, is 22.414689 liters. Again, we're limited to 3 sig figs. So I'm going to put these lines here to remind myself, but I'm going to wait to round till the very last step. So we're ready to calculate our density density of nitrogen gas is equal to mass over volume, right? And we have our mass is 28.02 grams, and this has 3 sig figs, over our volume, which is 22.414689 liters, and this is 3 sig figs. And so we divide 28.02 by this lengthy denominator to get a value, which is 1.25007311. All right, we can only keep 3 of our sig figs, so this is going to round to 1.25, and our units are grams per liter, and that is the density of 1 mole of nitrogen gas at standard temperature and pressure. All right. So those are the first 2 kind of introductory problems, examples where you can use the ideal gas law. But they're not the only ones, and there are indeed more advanced versions, and we're going to dive into one of those and then look at one last gas law, which is Dalton's law of partial pressures. And then we're going to call it a night. Whoa. I don't know why my computer just made that sound. Angela, you are correct. The molar volume of a gas will be limited to 3 sig figs because of the pressure, STP being 1.00 atmospheres. All right, so let's do a new example, kind of a next level problem. All right. So let's take a look at the following example. How about this? Nitrogen gas reacts with hydrogen gas to produce ammonia vapor, which is NH3 as a gas. This reaction takes place at 215.00 degrees Celsius. In a 15.0 liter reaction vessel. Sorry, one more piece of information. Under 1.25 atmospheres of pressure. Part A. Write a balanced chemical equation for this reaction. Part B. Determine the theoretical yield in grams of ammonia gas. And part C, if the percent yield is 67.2%, what was the actual yield? All right. So, let's start with part A. Let's write a balanced chemical equation for this reaction. We have nitrogen gas reacting with hydrogen gas to produce ammonia. So we have in this problem, in this reaction, we have nitrogen and hydrogen on both sides of this this reaction. So we've got 2 and 2 on the reactant side, 1 and 3 on the product side. You can see my 2-year-old is not much of a fan of stoichiometry, but then again, who is? So we need to multiply ammonia by 2, right, to balance out our nitrogen. So we have now 2 nitrogen on the product side and 6 hydrogen. To balance out hydrogen, we need to come back to the reactant side and multiply H2 by 3. And this gives us our balanced chemical equation. All right, so that is part A. Part B of this problem. Part B looks like quite an unfamiliar challenge. And again, I've said this before, but anytime you're in lecture and you don't know how to do an example problem, it is excellent preparation for the exam. There will be familiar problems on each exam, but there will be problems that you've never seen before. So this is a chance to kind of simulate that testing environment. How do you tackle a problem that you've never seen before? And briefly, I'm going to go back to that slide so that we can kind of survey and collect our thoughts. So one thing you'll notice is we are being asked to find the theoretical yield. All right, we're being asked to find a theoretical yield, and there are 2 types of theoretical yield problems that we've seen in this class. Therefore, there's one where you're given the initial quantity of one of the 2 reactants. The second, you're given the initial quantity of the hang on. This problem I need to add one thing, or I need to change one thing. Sorry, I realized with this problem that to solve this problem, we actually need to use we need one more piece of information, and we need to use Dalton's law of partial pressures, which I haven't taught you yet. So I'm going to make an addendum. I'm going to change this problem. Rather than give us the pressure, we'll do a problem like this in the future of this lecture. But rather than give us the pressure, I'm gonna change one thing. The vessel contains 0.78 or actually, we're going to go period there. Oh, come on. There we go. Sorry, Photoshop was lagging just a bit. So what I'm going to add is the pressure of hydrogen in the vessel is 0.78 atmospheres, and the pressure of nitrogen in the vessel is 0.47 atmospheres. All right, and now we have enough information to solve the problem. You'll see when we get to Dalton's law of partial pressures how you would handle it if you were given an overall pressure, but we're not there yet, so one step at a time. Now, here's the thing that when it comes to gases that you need to start kind of learning. This is the relationship that you want. You want this relationship to become second nature. When you look at the ideal gas law, PV equals nRT, you will always know R. All right? And so if you're given pressure, volume, and temperature of a gas, you will be able to find moles, and you'll be able to do stoichiometry. And one thing you'll notice is we're given the pressure of hydrogen and the pressure of nitrogen inside this vessel, and our temperatures, well, we're told that the whole thing is at one temperature, and the whole reaction vessel has one volume. And these apply to both nitrogen and hydrogen. It applies to every gas in the vessel. Every gas in the vessel is the same temperature, and every gas fills the vessel. A gas is an interesting phase of matter because it fills whatever volume it's stored in. So both of them have a volume of 15.0 liters, and both of them have a temperature of 215.00 degrees Celsius. All right, so we have the pressure, volume, and temperature of both nitrogen and hydrogen, which is another way of saying we have our initial quantities of both nitrogen and hydrogen, right? We can find our moles of each. Once we do that, we can set up a limiting reactant problem. Figure out which one's the limiting reactant, and that one will determine our theoretical yield. So we need to first use the ideal gas constants and the ideal gas law to find the moles of each, and then use those moles in a stoichiometric calculation. All right, so first let's find our moles of N2. We know that we've got PV equals nRT, and so if we divide both sides of this equation by RT, it rearranges so that we get moles. Our moles of gas are equal to pressure times volume over the ideal gas constant times temperature. Now, one thing that we want to, so we're going to use this equation, but I want to point something out. First off, so N is equal to P V over R times T. If you plug in your values, so we're given our pressure of nitrogen is 0.47 atmospheres. Our volume was 15.0 liters over our ideal gas constant 0.08206, and this is liter atmospheres per mole Kelvin times our temperature, which was 215.00 degrees Celsius. If you plug in these numbers as is, you'll notice that liters cancel liters, atmospheres cancel atmospheres, but you'll notice there's a problem. Our temperature unit in the ideal gas constant is Kelvin, and our temperature unit that was given was Celsius. These do not cancel, so we need to do a unit conversion before we can actually crunch our numbers. And the unit conversion to go from Celsius to Kelvin is you have to add 273.15 K. And often students ask me, can I just use 273.15? Or sorry, often they ask, can I just use 273? And the answer is no. Because the conversion factor is actually precise, 5 sig figs, 2 decimal places. Using 273 is like the high school version, but you're in general chemistry, you're in college chemistry now, and so if you don't use the full conversion factor, your numbers may be slightly off, and that may hurt you on the exam. So I don't recommend doing it. So 215 degrees Celsius is 488.15 Kelvin, and now our temperature units cancel. So now we can crunch our numbers. 0.47 times 15.0 divided by 0.08206 divided by 488.15. So we have our number of moles of nitrogen are 0.175996. We can only keep 2 sig figs though. So I'm going to put those there and there. As a reminder, that is our quantity of moles. For nitrogen, let's do the same calculation for hydrogen. So as we know, moles are equal to pressure times volume over R times T. Our pressure for hydrogen is different. We were told that the pressure of hydrogen is 0.78 atmospheres. Our volume is the same, 15 liters. The ideal gas constant is constant as always, 0.08206 liter atmospheres per mole Kelvin. And then our temperature in Kelvin, 488.15. Units cancel. Kelvin cancels Kelvin. Atmospheres cancel atmospheres. And liters cancel liters. We're left with moles, which is good because that is what we're solving for. And we have 0.78 times 15.0 divided by 0.08206 times 488.15. Whoa, I just did times. That should be divided by. Here, hang on. While I re-crunch my numbers. All right, so this comes out to be 0.292079 moles of hydrogen. And again, I can only keep 2 sig figs because that is the number I multiplied with the fewest only had 2. So now that I have my moles of both nitrogen and hydrogen, we can do our limiting reactant calculation because these are our initial quantities. I'm going to bring back my balanced chemical equation now because this is when we need it. Move it a little higher though. There we go. All right. So let's do our limiting reactant calculation. So we have 0.17599 technically. I should have rounded that up to a 7. Moles of nitrogen, and again this number has 2 sig figs. We need to convert from moles of N2 to moles of NH3, and the ratio here is 1 mole of nitrogen produces 2 moles of ammonia. Moles of nitrogen cancel. Next, we need to convert from moles of moles of ammonia to grams. And nitrogen has an atomic mass of 14.01. Hydrogen has an atomic mass of 1.008. We got 3 of them. So crunching these numbers, 1.008 times 3 plus 14.01 gives us an atomic mass of 17.034. Our last significant digit has to be in the second decimal place. We're going to use the whole number without rounding, but I'm going to put that mark there to remind myself that that is the last sig fig in the number. All right. Hi, Sean. I will totally answer your question, but after concluding the gas laws lecture, so probably in another, looking at where we are, I'd say like 30 to maybe 40 minutes on the long end. Once I finish the gas laws lecture, then office hours will be up and rolling. All right, so molecular mass of 17.034 with our last sig fig right there. Now moles of ammonia cancels, and we're ready to crunch our numbers. 0.175997 times 2 times 17.034 gives us, let's see, well, 5.996, but when you round it to 2 sig figs, that'll be 6.0 grams of ammonia. But we don't know if this is our answer, right? This is a limiting reactant calculation. So we need to see what our limiting reactant is before we know our theoretical yield. And to do that, we need to repeat this calculation using the moles of hydrogen gas we just calculated. And also this quantity has 2 sig figs. Step number 1, we got to convert from moles of hydrogen to moles of ammonia. And that ratio we get from the balanced chemical equation. 3 moles of hydrogen produce 2 moles of ammonia. So moles of hydrogen cancel. Next we use the molecular mass of ammonia that we just calculated in the previous step. To get our grams of ammonia. Angela, that is a great question. Here's the deal. Angela, there will always be enough information given to solve the problem. There's 5 variables, right? So if you're given 3 variables, then you usually need another equation to solve. But I'll show you an example that's kind of interesting where you can be given 3 out of 5 and still find your answer. So you can rest assured that you'll always be given enough to calculate the answer to solve the problem. But it may not always be as straightforward as being given 4 out of 5 variables. And I'll show you what I mean in just a moment. All right, so I'm getting 3.3168. We can only keep 2 sig figs. Totally, you are welcome. So this is 3.3 grams of ammonia. And the thing is, in a limiting reactant scenario, we do the calculation for each quantity of starting material, and whichever one is smaller, that is our theoretical yield. Making hydrogen our limiting reactant. All right? So that is the answer to part B. Let's go ahead and take a look at part C. All right, part C of this problem tells us our percent yield was 67.2% and asks us to find the actual yield. All right, and this all hinges on the equation for percent yield. Percent yield is actual over theoretical times 100. And when you look at this equation, we have been given the percent yield, right? We are literally just given the percent yield right here. But then we found the theoretical yield in part B. So we have the percent yield, we have the actual, we have the percent, we have the theoretical, we can solve for our actual yield. So percent yield is 67.2 is equal, I should move this down just a hair. Is equal to actual over theoretical, which was 3.3 grams, times 100. Well, to solve for our actual yield, we need to cancel our 3.3 and our 100, right? We need to isolate our actual yield on one side of this equation. So 100 cancels, 3.3 grams cancel. And we can crunch our numbers. So 3.3 times 67.2 divided by 100. We can only keep 2 sig figs, so our actual yield of ammonia is 2.2 grams. All right, and that is the answer for part C. Okay, Allison, you asked a very interesting question. All right, very interesting question. And your question was, so when you're using the ideal gas law, PV equals nRT. Are we always, you'll notice that in the ideal gas law, there are 5 variables. Right? We have, hang on. Right, 5 variables. Okay? And so if, algebraically speaking, you can solve, so there's a few scenarios. One, if you're given 4, you can solve for the 5th, right? That's just algebra. That's one scenario. Second scenario, you could be given 3 plus an equation. Oops, not a qual. Equation. And solve for the 5th. Right, and the reason why you need this equation is this equation will give you number 4, right, the 4th variable. So that's another way, is you could be given 3 and then another equation that lets you find the 4th and then you find the 5th. But a third is an example like the following. A gas what is the molarity of a gas at 335.70 Kelvin and 2.80 atmospheres. This one may look a little bonkers because you're given temperature, you're given pressure, and you always know R, and that's it. But I'm asking you to find molarity, and this one might seem a little nuts because you're like, well, PV equals nRT. You haven't told me anything about volume. You haven't told me anything about my moles. So how am I, and you haven't given me anything else to go on. How am I supposed to solve this? And you can solve it with a little bit of tricky algebra. Check this out. What is molarity? Molarity is moles over liters, right? Molarity is moles over volume. Both of these things are present in the ideal gas law, am I right? It's PV equals NRT. Watch what happens. Let's divide both sides of this by RT. That's something that we've done before. Right? They'll cancel over here. And we'll get moles are equal to pressure times volume over RT. Now, let's multiply both sides by 1 over V. Volume cancels out of my right side. And what do I get? I get N over V, moles over volume, are equal to pressure over R times temperature. Now what is moles over liters? That is molarity. And I have, in this problem, been given pressure and temperature, and I always know R. So let's calculate our molarity here. Our pressure that we were given here, I'm just going to peak 2.80 atmospheres over R 0.08206 liter atmospheres per mole Kelvin times temperature, which I don't remember what I wrote on the previous slide. My apologies. 335.70. Whoa, that's not what I meant to do. There we go. And watch what happens. Kelvin cancels Kelvin. Atmospheres cancel atmospheres. Crunch your numbers. 2.8 divided by 0.08, 0.08206 divided by, hang on, 2.80 divided by 0.08206 divided by 335.7. So my molarity, moles over volume, right? Moles over liters is equal to 0.102 moles per liter. So, Angela, Angelina, that would be an example of I only give you 3 variables, but technically it's the first instance, right? Because you use another equation, the equation for molarity, to come in with a little bit of extra information, shine a light on the problem, and get to an answer. So, in general, if you have one equation, you have to be given, you can solve for one variable if you're given the rest. If you're not given the rest, then that means there's some other equation that you got to bring in to help you with the problem. This one's very tricky though. This is but you might see something like that on exam 3. Again, this won't be on exam 2, but it will be on the 3rd one. So that is an excellent question. Thank you for asking it. All right, we're gonna march forward. There is one last gas law that we have to talk about before office hours can start, and that is Dalton's law of partial pressures. Dalton's law of partial pressures. Dalton's law of partial pressures has two formulations. It basically states that a mixture of gases, the total pressure of a mixture of gases, is equal to the individual the partial pressure of each individual gas added up. One way of saying it is you can write it like this. The total pressure of a mixture of gas is equal to the partial pressure of the first gas plus the partial pressure of the second gas plus ... the partial pressure of the nth gas, however many gases are present in this mixture. All right, so that's one formulation of Dalton's law of partial pressures. Another way of writing it, so this is one way of writing it. Another way of writing Dalton's law of partial pressures is like so. The partial pressure of gas number one in this mixture of gases is equal to what we call the mole fraction for gas number one times the total pressure. And this thing right here, so this is called the mole fraction. And the mole fraction is that's a Greek capital chi, Greek letter. The mole fraction for gas number one is a ratio of the moles of gas number one present in the mixture over the total moles. So this is right here, moles of gas one right here, and this is total moles. Right down here. And this, just I guess for completeness, is the total pressure. All right, these are the two ways of writing Dalton's law of partial pressures. They're useful in different contexts. You'll probably use both of them as you go through the homework. Where you see it kind of played out or used is often, and actually this will tie into what we're about to talk about in lecture on Wednesday. We're going to be talking about gas evolving reactions for acids and bases. Angelina, I am glad you think so. The tricky ones, I do think they're more interesting as well. So, Dalton's law of partial pressures ties in with this general kind of class of problem for reactions where gases are collected over water. All right, gases collected over water. So, for example, you will learn that when you react an acid like hydrochloric acid, or actually, let's make it even more, acetic acid will react with sodium bicarbonate, also aqueous, to produce water, which is a liquid, sodium acetate, and CO2 gas. This is a reaction that probably everyone who's been through elementary school has experience with. This is a reaction. This is the classic baking soda and vinegar volcano, right? Acetic acid is vinegar, or it's the acidic part of vinegar. Baking soda is just straight up sodium carbonate, and you mix these two. I apologize for that yawn. I tried to stifle it, but I couldn't. It's not because I think that acetic acid baking soda volcanoes are boring, because I think those are awesome. You mix these two and it makes water and a salt. This is aqueous. Forgot to add a phase there. And a gas. Right, this is, and again, we'll talk about this in lecture on Wednesday. This is an example of a gas evolving reaction. Anytime a bicarbonate reacts with an acid, it's going to make carbon dioxide gas. Now, here's the thing, and this is the tricky thing. It may look like there's only one gas produced by this reaction, and technically there is only one gas produced by this reaction. All right, carbon dioxide is the only gas produced, but it's not the. It is actually produced not as pure CO2, but as a mixture. All right, so let me set up a visual aid. All right, so if we have a reaction vessel here where we have the in here we've got the HCl and the acetic acid, not HCl, excuse me, the acetic acid, and we've got the sodium bicarbonate, all right, so these two are present in this solution. And as they react, they start to form bubbles of carbon dioxide. You've seen this go down. You know what happens. And if we have a pipe that carries the CO2 to a balloon, and as the CO2 kind of moves through the pipe, it goes up in there, it's pushing its way through, it's going to inflate this balloon, right? And the thing is, it's not pure carbon dioxide. It's not, because there's this thing called vapor pressure. You'll notice that all of our reactants and products, well, both of our reactants are in the aqueous phase. The products, one's aqueous, one's liquid water, the other CO2 gas. Whenever you have liquid water, if you have a cup of liquid water and you leave it on your counter, you go vacation for a weekend, right? Take a long weekend, come back. Is there still going to be water in that cup? Part of it depends upon how big the cup is, right? But if it's a small cup, it's going to be bone dry. What happened to the water? Well, you know what happened. It evaporated, right? It evaporated out. That's because under atmospheric pressure and at room temperature, water is slowly leaving the liquid phase and joining the gas phase. So there's actually, as the CO2 leaves and travels, water vapor is leaving and traveling with it. So the atmospheric pressure is actually equal to the partial pressure of CO2 gas plus the partial pressure of that water vapor that is mixing with the CO2 gas as it bubbles out of solution. Anytime, and this is the take-home message, anytime, and we will see plenty of examples of this, anytime a gas forms, in the presence of aqueous solutions, that gas is collected as a mixture. All right, it'll always be collected as a mixture of whatever that gas is plus water vapor, which is slowly evaporating with the gas as it is produced. All right, and so that leads us to this type of problem that is quite a challenge, but this is exam caliber. You're guaranteed to run into problems like this, of this nature, of this challenge level, on exam 3, not exam 2. Doesn't have chapter 5, but exam 3. You're going to hit problems like the following. So let's take a look. Solid zinc metal reacts with aqueous hydrochloric acid to produce zinc 2 chloride and hydrogen gas. The gas is collected over water and occupies a volume of 65.0 milliliters. If this reaction takes place at 25.00 degrees Celsius, and atmospheric pressure is, 0.92 atmospheres, how many grams of zinc metal reacted? All right. Now, one thing I want to point out, there's a piece of information that's missing from this problem. And on the exam, I will totally give it to you, and I'm going to give it to you here. But when you're doing homework problems in the book, they won't give this to you. So, quick thing, note. The vapor pressure of water at 25.00 degrees Celsius is, let's see. Where do I have? Oh, there we go. I knew I had it written down. Is 17.55 torr. All right. Now, the reason why this wasn't included in the original problem is because when you're doing homework problems, they won't give you the vapor pressure of water. The vapor pressure of water is different at every temperature, so you have to look it up in a table. The homework problems don't give it to you. So when you're doing a problem where gas is collected over water, you got to go find that table, find the vapor pressure at the temperature that reaction is taking place in, and use that value. On the exam, I will provide it for you, so you don't have to have a table for vapor pressure of water. I'll include it in the problem as I've done here. But that's just one thing to note about the homework. They don't give that to you. You got to look it up. So if you're doing a problem like this and you are stuck, you're like, I feel like I'm missing a piece of information. This will help you remember, wait a minute, I need to look up my vapor pressure for water to solve this thing. All right, now, so you may be looking at this problem, and again, you may feel overwhelmed. Don't be. If you're watching this video later, pause it. I would pause right here. Try to do this on your own. You're going to get stuck, but that's good, because then you unpause the video, watch me take steps, that'll get you unstuck, pause it again, see how much farther you can make it, see how well you can do this on your own. Now, we're going to need a reaction here, right? We're told that we've got zinc metal reacting with hydrochloric acid to produce zinc chloride, zinc 2 chloride, and hydrogen gas. All right. We're given a bunch of information about the gas that's formed. We're told a volume. We're told a temperature. We're even given a pressure, right? Which we'll see how to use that in a minute. So we've got some things to go on, and then we're asked to find grams of product. So this is clearly a stoichiometry problem. To do any stoichiometry problem, we need to write a balanced chemical equation. So things have to start there. We have a reaction between solid zinc metal, right? So that's not a gas, that's a solid. And it's just zinc. It's not a compound, it's just zinc atoms. Reacting with aqueous, hydrochloric acid. Let's take a moment here. This will be good review. hydrochloric acid. Whenever you have a hydroic acid, that means your anion ends in "ide." So the anion we're dealing with here is chloride, Cl minus. All right? If chloride has a charge of -1, that means that hydrochloric acid will have one hydrogen, right? The acid gets one hydrogen for each charge, for each negative charge that the anion bears. So we have zinc plus HCl, which is aqueous, produces, all right, it produces zinc 2 chloride. Now we already know chloride's charge is -1. Zinc is a transition metal, which is why we're given the charge. It has a charge of +2. So zinc 2 chloride would be ZnCl2. And this is aqueous because chlorine is usually soluble. It's only insoluble with mercury 1, lead 2, and silver 1. So zinc's not on that list, meaning zinc 2 chloride is soluble. The last product is hydrogen gas, and hydrogen is one of our homonuclear diatomics, so it is H2 gas. Oops. So there's our chemical equation. Now we need to balance it. So we have zinc, hydrogen, and chlorine. Zinc, hydrogen, and chlorine. On our reactant side, there's 1 zinc, 1 hydrogen, 1 chlorine. On our product side, there's 1 zinc, 2 hydrogen, 2 chlorine. So we can balance this whole thing if we multiply HCl by 2. Right? This will balance hydrogen and chlorine in one foul swoop. So that is our balanced chemical equation. All right, now let's start thinking about what we need to do to solve this problem. We were asked to find grams of zinc, right? And we've been given a ton of information about hydrogen, right? We know the volume of hydrogen is 65.0 mils, right? Looking now to PV equals nRT, right? That gives us a volume. We're also told a temperature, right? We're told the temperature is 25.00 degrees Celsius. Now, we're going to have to convert that, right? But all things being equal, we know the temperature. We always know R, right? R is the ideal gas constant. It's 0.08206 liter atmospheres per mole Kelvin. Angelina, great question. And the answer is no. All it takes is 1 aqueous reactant or product. 1 aqueous reactant or product, and you will be dealing with water vapor. So, so as you can see with this problem, we've got 1 aqueous reactant, 1 solid reactant. We still have to deal with water vapor. All right, now here's the thing. You can see where I'm going in this problem, right? You can see where I'm going. We want to get to moles of hydrogen so that we can do stoichiometry. Here's where you have to be careful. The pressure we were given in this problem, so we need pressure of hydrogen. The pressure that we were given in this problem, which was 0.92 atmospheres is not the pressure of hydrogen. This is a total pressure. This is equal to the pressure of hydrogen plus the pressure, of water. Because this takes place in an aqueous solution, because it was collected over water, that atmospheric pressure is actually equal to the partial pressure of H plus the partial pressure of H2O. So we need to solve for the partial pressure of H2, and we can do that if we subtract both sides of this equation. If we subtract the partial pressure of water from both sides of this equation, that gives us an expression 0.92 atmospheres minus the partial pressure of water equals the partial pressure of hydrogen. Now, what is the partial pressure of water? It's that vapor pressure we were given. Problem is, the vapor pressure we were given was given to us in torr. So we need to do a unit conversion. I need to clear a little space on this board. Let me rearrange things just a tad. Then I can pull this over. So the partial pressure of water is given to us in torr. We need it to be consistent with our atmospheric pressure, which was given to us in atmospheres. So the unit conversion to go from torr to atmosphere is 1 atmosphere is 760 torr, and that is exact. So 17.55 divided by 760 is 0.02309 atmospheres. So now our partial pressure of hydrogen is equal to 0.92 minus 0.92 ATM minus 0.02309 ATM so my partial pressure for hydrogen is 0.89691, but I have to round to the second decimal place, and when I do, I get a partial pressure of 0.90 atmospheres. This is now the value I can plug in to PV equals nRT to find my moles of hydrogen. Once I do, I can use my balanced chemical equation to find the mass of zinc. All right, so let's do some stuff. Let's do some algebra. We have PV equals nRT. We're going to rearrange this. To find our moles. So we get moles of hydrogen. To be specific, it's equal to PV over RT. we just found our pressure, 0.90 atmospheres. Our volume, 65.0 milliliters, over R, 0.08206 liter atmospheres per mole Kelvin. And our temperature, 25.00 degrees Celsius. All right, now, we're not ready to crunch our numbers. We're not quite ready. You'll notice that atmospheres cancel with atmospheres. That's good. But we've got two problems. One problem is we have different temperature units. The second problem is we have different volume units, liters and milliliters. Now, this is the reason. You may have noticed that I kind of meticulously always include units when I'm doing these problems. The reason why is often when I found this as a student, I would get to the end of a problem and my mind would be getting tired and I'd just be like, okay, let's punch this in, let's get the answer. And I would forget things like, oh, I need to convert milliliters to liters, so they're both the same. I need to convert Celsius to Kelvin, so they're both the same. And I found that if I just plugged my units in every time, that would stop me from making that mistake, because I'd get to this point and I'd be like, oh, wait, I can't cancel liters and milliliters. I need to convert that. I can't cancel Kelvin and Celsius. I need to convert that. So it's just a way, a stopgap to prevent me from losing points needlessly. Angelina, great question. So the previous problem was a gas evolving reaction between an acid and a bicarbonate salt, and that type of reaction always produces water. It happens in aqueous media, and water is a product. But you'll notice water vapor wasn't a product. The product was actually liquid water. With this reaction, this is a reaction between HCl, hydrochloric acid, and solid zinc metal. And the products here are zinc chloride, which is aqueous, and hydrogen gas. The thing is, you will be dealing with water vapor anytime you're doing a reaction, working a problem where one of your reactants or products are aqueous. If it's in aqueous media, that means there's a solution of water, and wherever there's water, it's slowly evaporating. So there is a vapor pressure of water that you have to take into consideration every time you have a gas being formed in the presence of something in the aqueous phase. So even if water is not a product of the reaction, if you have aqueous media, you've got to account for the vapor pressure of water. All right. Okay, so that being said, we've got a couple unit conversions to do. First, we got to convert from milliliters to liters. You are so totally welcome. And I so appreciate your questions too. And I know that probably a lot of people aren't watching because they're like, this is exam 2 material. And people want to focus on exam 1. I totally get it. But they will be grateful for your questions, because I guarantee that many people will have the same ones you're asking, and you being here, being present, and voicing them gives me a chance to address those, and it's going to make the lecture a lot more clear for students who watch it in the future, not live. So thank you for being here and contributing so positively. So we put milliliters in the denominator, liters in the numerator. 1 milliliter is 10 to the negative 3 liters. So mils cancel, and this will be equal to 0.0650 liters. And then the converting 25.00 degrees Celsius to Kelvin, we got to add 273.15, and that'll get us to 298.15 Kelvin. All right, now we can plug these numbers in and actually get an answer. So 0.90 atmospheres times 0.0650 liters over 0.08206 liter atmospheres per mole Kelvin times 298.15 K. All right. Okay. Let's see. Atmospheres cancel, as we know they would. Liters, our volume units, now cancel, which is delightful, and our temperature units cancel as well, leaving us just with moles. So now we're good to crunch our numbers. 0.9 times 0.065 divided by 0.08206 divided by 298.15 gives us our quantity in moles. Hang on, my chat just went offline. Just gotta get this troubleshooting the network. Okay. So that means that we have, and let's see, we can keep 2 sig figs because of our pressure has 2 sig figs. So we have 0.002391105 moles of hydrogen. We can only keep 2 of our sig figs, but I'm going to wait to round because we're not done with this problem yet. We need to find our grams of zinc. So we got to convert moles of hydrogen to moles of zinc. And that conversion factor is right here. It is a 1-to-1 ratio. Moles of H2 cancel. Next, we need a conversion factor. So this should be Zn. 1 mole of zinc. And here we just look straight up, look at the periodic table. So zinc has an atomic mass of 65.41 grams in 1 mole. Moles cancel. And now we crunch our numbers. So I'm getting 0.156398 grams of zinc. And we get 2 sig figs. The 6 will round up. So our final answer is 0.16 grams of zinc reacted. All right, that is a beast of a problem. It is a beast of a problem, but it is probably the most true-to-life application of Dalton's law of partial pressures I can come up with. It's very, very, it's a practical application because we do a lot with reactions that form gases, and in Gen Chem, all our reactions are in aqueous media over aqueous media. So it just comes up a lot. So this is definitely material you can expect on exam 3. This is definitely the kind of stuff you want to be practicing. All right, well, shoot. That brings me to a conclusion of my second lecture of chapter 5. I said I was going to go like an hour, and it looks like I went an hour and 40. Which I guess, since I went an hour the first time, it's like two 80-minute lectures when you think about it, when you line them up back to back. I guess I just saved more of the hard stuff. For the second lecture. All right, so end of chapter 5 lecture, beginning of office hours. Sean, you have been a patient dude. I'm ready to answer your question. Okay, so let's see. For lab 3, okay, hang on one second. Let me just pull up some stuff. All right, let's see. Okay, so Sean, for ELAB 3, tried mixing magnesium with sodium sulfide, resulted. Whoa! Okay, Sean, I'm so sorry. Okay, so I'm laughing because you may have found a glitch in the Beyond Labs software. So, if you were mixing magnesium cations with sodium sulfide, all right. So we know, right, because this is aqueous, that those two ions aren't associated. So we're going to get Mg2+. We could rewrite it like so. 2 sodium cations plus sulfide anions. And we know that when you combine magnesium with sulfide, sulfide is usually insoluble. It's soluble when you mix them with calcium, strontium, or barium. Magnesium's not on that list. So this will make a solid precipitate, which is solid magnesium sulfide. All right. Now, that should be the product, plus you should get, your spectator ion, right? Sodium. One thing that should not be the product is magnesium hydroxide. Right? Hydroxide is nowhere in this reaction. That is not the product. All right. So yeah. The product should be solid. You should get a solid precipitate, but it won't. There's not some weird voodoo reaction that you've never seen before going on. That is a glitch in the Beyond Labs software. Totally. So that is that. I'm going to. I know I got like at least one email. I'm going to check to see if I got any more sent in. But at this point, office hours are live, and I will totally hit up the live questions ahead of the emailed ones. But in the absence of live questions, I'm going to slowly start churning through these emails. Okay. Yes. Okay. The first one is actually a question about exercise 3 that I can answer. So the first question one. So there's a question on there that says that talks about a monoprotic acid. All right, and that is an acid that just has one hydrogen to donate. So if you have a monoprotic acid named HA reacting with sodium hydroxide, that means it will produce water, H2O, and the salt, NaA, right? And so the point here is in the balanced chemical equation, there is a 1-to-1 ratio between HA and sodium hydroxide, and that is what you need to solve that problem. Okay, let's see. Okay, it looks there are a couple questions on exercise 3 that might be typos. I'm not sure. I'm gonna pull it up here and have a look. That one either. Hang on. There it is. Okay. Hang on, I'm getting to it. I just have a ton of problem banks, and Canvas is not. It's fine, but navigating through them is not the most user-friendly experience. All right. Okay. Let's see. I'm checking in on potential typos. Ah. Okay. Okay. Let's see here. All right. So there was a. So I looked into the first one, and there totally is. Oh, hang on. Let me. Wait, no. Um. There totally is a typo on this problem. Let me go. There we go. Oh, you know what? about another problem? Bum. Done. And let's see. Let's see. So I'm looking into this other potential typo. Yep. There is a second typo. All right, I found. Let me see. Exercise 3. For the problem asking the masses of two excess reactants on the left. Okay. Let me. All right. That is an excellent question. So here's how you would approach that problem. So here's the deal. I'm going to, Afan, that is a great question, and I am going to do a problem that is similar but different. So consider a reaction between nitrogen and hydrogen gas to produce ammonia. And let's say that we mix 2.0 grams of each. And I am asking you the question. Determine the mass of excess reactant after the reaction is complete. All right, so here's the thing. First, this is kind of like a limiting reactant problem in that you need to know what the limiting reactant is, because one of these is the limiting reactant, the other one is the excess reactant. All right, so you're going to need to do that first and foremost. All right, first, step 1, find the limiting and excess reactants. All right, that's step one. And here's why you need to do that. To find the amount that's left over, you follow this equation, this thought process. So you have some initial amount. Whoa. Don't know what's going on there. You've got some initial quantity of grams. You need to subtract the grams that react. And when you take the difference between your initial quantity and the grams that react, that difference will be your excess grams. All right? Now, your initial quantity is going to be whichever one is excess, however much you start with. All right? So you're given that. The amount that reacts, hang on. The amount that reacts, so that quantity that you're going to subtract, we need to calculate this. You got to calculate it from the limiting reactant, all right? So that's why you need to know what the limiting and excess reactants are. So step number one, find the limiting reactant. Step number two, you're going to calculate the grams of excess reactant that reacts. And then number three, to find the mass of excess reactant left over, you take the difference, which is this whole situation right here. All right, so this is the three-step process. Step number one, we need to know what the limiting and excess reactants are. So we've got to do this tried, what hopefully is starting to feel like a familiar process. So step number one, we got to convert grams of nitrogen gas to moles. We do that by dividing by the molecular weight. Next, we convert from moles of N2 to moles of our product. And in this problem, we're not actually interested in the amount, the grams of ammonia that are formed, so we can just stop at moles. No reason to do more work than is needed. Grams of nitrogen cancel grams of nitrogen. Moles of nitrogen cancel moles of nitrogen. And let's see here. We have 2 divided by 28.02 times 3 gives us 0.21 moles of ammonia. This is only useful in that it'll tell us what our limiting reactant is and what our excess reactant is. So next we got to convert from grams of hydrogen to moles of hydrogen followed by converting from moles of hydrogen to moles of ammonia. Say 3 to 2 ratio. Moles of hydrogen cancel with moles of hydrogen. Grams of whoa, it's a wide circle. Grams of hydrogen cancel grams of hydrogen. So we got 2 divided by 2.106 times 2 divided by 3. This is 0.66 moles of NH3. So because this is smaller, that means nitrogen is the limiting reactant, and because this quantity of moles is larger, that means hydrogen is the excess reactant. All right? So we have determined that hydrogen is the excess reactant. Now we need to know how much hydrogen is consumed. All right? And to find, so we're trying to find the grams of hydrogen that reacts. To do that, you have to take your mass of your limiting reactants and convert it to grams of excess reactants. Right, because we want to know the amount of hydrogen that will react with this mass of nitrogen. So you convert grams to moles of nitrogen, then you convert from moles of nitrogen, sorry, that's not normal, 1 to moles of hydrogen, followed by going from moles of hydrogen to grams. Now our mass of hydrogen cancels, or sorry, nitrogen cancels. Moles of nitrogen cancel. And then moles of hydrogen cancel. So we can calculate the mass of hydrogen that reacts. So 2 divided by 28.02 times 3 times 2.016 equals 0.43 grams of hydrogen. That is the quantity that reacts. Now, that was step number 2. This is step number 3. You take your initial, that's, we started with 2.0 grams, subtract 0.43, the amount of hydrogen that reacts, and we're going to be left with let's see, 1.57, but sig figs wise, our least precise was our initial, so we've got to end at the first decimal place, so our final answer will be 1.6 grams of H2 are unreacted. This is left in excess. Let's see. Right, I don't think they give 2 billion pounds. I think that, but they do give a very large quantity in grams. Here, let me check. Let me check Canvas. Ha! Oh, man. Okay. Gotcha. Dude, so, let's... Oh, dude, you totally don't have to. Okay, Stephanie. I see your question. Um, so Rin, great question. Um, Rin, I can't discuss specific answers. So like, I can't do that thing where you can be like, is the answer this? I can't say yes or no because it's an assigned, it's a graded assignment. However, I can totally explain how to approach a specific problem if you're stuck or struggling with one in particular. I can talk about how to approach it. I can also even work a similar problem, maybe change the numbers around or do something like that. So you can totally ask questions about exam packet 1, and if you want to direct me to a problem in particular, I can look it up and either give you some pointers or do a similar problem that's similar but different. So you let me know what you would like some help on. Okay, problem 6. Let me pull that up real quick. Problem 4, 5, 6. Okay, let's see. Percent weight of fluorine in CH3F is 55.83%. If there are 0.168 grams of fluorine in a sample of CH3F, how many molecules of fluorine are in the sample? Okay, this is a great problem. Great problem. And here's what I'm going to do. I'm going to do this problem. I'm just going to tweak it. All right, so I am going to do the percent weight of fluorine, which is the same as percent mass, by the way. I don't know if that's tripping you up. Is 55.8. Sorry, there's a second. 83% in CH3F. So I'm just gonna pick a different mass. I'm gonna say if there are, I'm just gonna go 5.93 grams of fluorine in a sample of fluoroforms. What this guy's? No, it's not. That's not fluoroform. This is monofluoromethane. Excuse me. Comma. How many molecules are in that sample? Question. Okay, so this solving this problem boils down to remembering what this percent mass is all about. This is a ratio. All right, this is a ratio that tells you that there are 55.83 grams of fluorine in 100 grams of CH3F. But like any ratios, you can invert it and it's still true because it's an identity. It's one. It's well, it's not. No, I take that back. I'm deliriously tired. It's not an identity, but it is a ratio, and it's true whether you invert it or not. There are 55.83 grams of fluorine in 100 grams of CH3F. You could also say that 100 grams of CH3F have 55.83 grams of fluorine within it. And you'll notice that if you multiply your mass of fluorine by the second ratio, look what cancels. Grams of fluorine cancel grams of fluorine. And what are you left with? Well, we can crunch these numbers. Let me grab my calculator. So when we crunch our numbers, so we got 100 divided by 55.83 times 5.93. This tells us that in our total sample has a mass of 10.6215 grams. All right. Now we can only keep 3 sig figs because of this mass. 1, 2, 3. But this is the key to solving the problem, because we're here asked how many molecules are in the sample, and now we've just determined the grams that are in the sample. And so we need to take that mass, 10.6215, and convert from grams to moles. So we need to put grams of CH, well, it's going to be a couple steps. Grams of CH3F in the denominator, moles in the numerator. So we have a molecular weight to calculate. Carbon is a mass of 12.01. Hydrogen, 1.008. Fluorine, 19.00. We have 3 hydrogens in the mix here. So 1.008 times 3 plus 12.01 plus 19 is 34.034. Remembering that this has 3 sig figs and this has 4. Now grams of CH3F cancel, and now we can convert in the final step from moles to molecules using Avogadro's number. So there's that many molecules in 1 mole. So we got 10.6215 divided by 34.034 times 6.022 times 10 to the 23rd is 1 point, let's see, rounding to 3 sig figs, 8 times 10 to the 23rd molecules. CH3F. All right, so Rin, that is how you approach problem 6. All right, Ludwig, let's see. You are stuck on problem 9. Let me take a look. All right. This one, I believe, or in my opinion, is the hardest one in this packet. So oh, dude. That is what I am here for. Okay, Ludwig. Okay, so with this guy, I'm not going to do every step of this, but I'm going to give you kind of a start on this one because I don't want to spill these beans explicitly. But let's see if we can kickstart this for you. Give it a whirl on your own. If it still doesn't make sense, shoot me an email, or drop by office hours on Wednesday and we'll dig more into it. But see if this is enough to get you started. So hydrogen represents 11.18% of the mass of a molecule with the chemical formula CzH6. Determine the value for Z. All right. So let's think about the key to solving this problem. Is your percentage of hydrogen and the chemical formula given. All right? So think about what the percent mass of hydrogen is, that equation. It's 6 times the atomic mass of hydrogen, right? Divided by 6 times the atomic mass of hydrogen plus Z times the atomic mass for carbon times 100. Right, that's what the percent mass is. And guess what? You know the percent mass. You've got to find this variable. So really, solving this problem simply comes from writing out the equation for percent mass of hydrogen and then doing some algebra. And this harkens back to something that I've mentioned in class. Anytime you're given a value where that value corresponds to an equation, it is 100% worth your time to write out what that equation is, because that equation will become a roadmap for solving the problem. So this is a great example of that, where it looks like an unsolvable problem. What do? You've never seen anything like this before, but you write out the equation and you'll be able to solve it. So take a stab at this. If you're still struggling, come Wednesday, shoot me an email or show up in office hours, and I will do not this explicit problem, because I can't give away answers to a graded assignment, but I will do a problem that is similar every step in all its gory details. But I think you'll get more out of it if you can get this on your own. All right, let's see. Question 3. Got grams of carbon, but I'm not sure where to go from there. Tried a few things, couldn't quite figure it out. Okay, let me take a look. Okay. Rin, if you got the mass of carbon, then you're super close. All right? So, here, you're trying to find the milliliters, right, of carbon. And you're given, in this problem, you're given the molecules of carbon, which you astutely use to find grams of carbon, and you're given the density of carbon, of graphite, which is 2.26 grams per cubic centimeter. All right? Now, you're going to see a common theme, actually, even with the problem that I just did. You've been given density, and density has an algebraic expression. You've been given a value for density, but density has an equation, right? Density is equal to grams over volume. I will stop being EHG at this moment. Grams per milliliter even. Something you should note, and this may be part of where you're stuck, but cubic centimeters often they're called cc's, is a volume unit, and it's equal to milliliters. When you look at this equation for density, when you look at this equation, you've been given density and you found grams, so you need to use the equation for density to find milliliters in your denominator. So you're just a little bit of algebra away from finding the milliliters. And again, it is probably the single most useful skill I can impart to you, to everyone in this class, is write out the equation for every value that has one. So like, if you're given a molarity, write out the equation for molarity. Given a density, write out the equation for density. Given a percent mass, write out that equation too. It'll lead you, it'll be a roadmap leading you to the answer. Rin, you are so welcome. And thank you for coming. Thank you for adding your questions to office hours. You made it better for me and for everyone else who's going to watch this in the future. It is 10, so I'm going to sign off here. I will catch you guys all on Wednesday afternoon, and then again on Wednesday evening, back here for office hours. Later, dudes.